Hello everyone, welcome to Homework Help. If you find the videos useful, please subscribe to the channel. So in this video, we'll sketch this function which is given as s at t equals t plus 1 over t. Now the first step is to combine the two terms in this function. So we know that the denominator of t is 1. So the common denominator will be t. So we'll multiply the numerator and the denominator of the first fraction by t to get the common denominator t. So we get s at t equals t squared over t plus 1 over t, which can be simplified to just s at t equals t squared plus 1 over t. Now this is a rational function. The first step is to find the discontinuities in this function. Now discontinuities in a rational function exist in the form of a whole or vertical asymptote. Now in this function there is no factor that's common to the numerator and the denominator, so this function has no whole. For vertical asymptote, we should set the denominator equal to 0. So we get t equals 0. So this is the vertical asymptote in this rational function. Now we have to analyze the behavior of the curve of this function on both sides of this vertical asymptote. So we can use the limit. So limit on the left side of t equals 0. So limit t approaches 0 from the left side. So t squared plus 1 over t. Now if we sub in a negative value, because on the left side of 0 the t values will be negative, so the numerator will become positive because t squared will give us a positive value and t squared plus 1 will also be a positive value, but the denominator will be a negative value, so the overall value for this limit will be negative. Now we can analyze the limit on the right side of this asymptote. So 0 from the right side. So t values on the right side of 0 will be positive values. So the numerator will be positive, the denominator will be positive, so the overall value will be positive. So now we can write the behavior of the curve around the asymptote. So as t approaches 0 from the left side, so the function s approaches negative infinity. And as t approaches 0 from the right side, so the function s approaches positive infinity. So that's the end behavior around the vertical asymptote. So now we can find the intercepts. So let's start with the t-intercept. So to find the t-intercept, we should sub in the function value as 0. So we get 0 equals t squared plus 1 over t. Now we can cross multiply the denominator. So we get 0 equals t squared plus 1. Now we can subtract 1 from both sides. The ones on the right side get cancelled out. So we get negative 1 equals t squared. Now square of t cannot be equal to a negative number. That means this function has no t-intercept. Now we can find the s-intercepts. So for s-intercepts, we should sub in t as 0 in the function. So s at 0 equals 0 squared plus 1 over 0. Now since 0 is in the denominator, that means this function value is undefined at t equals 0. That means there is no s-intercept. Next, we have to find the critical points for this function. So we have to find the derivative of the function. Now the s function is a rational function, so we can use the quotient rule. So prime of s at t equals, so we'll start with the derivative of the numerator, which is 2t plus 0 times the denominator, which is t, minus the numerator t squared plus 1 times the derivative of the denominator, which is 1 over the square of the denominator. So now we can simplify the expression in the numerator. So 2t plus 0 is just 2t. So 2t times t will be 2t squared minus, now t squared plus 1 times 1 will be t squared plus 1, and we can distribute the negative sign in the parentheses. So we get negative t squared minus 1 over t squared. So now we can combine like terms in the numerator. So 2t squared minus t squared is equal to t squared minus 1 over t squared. Now critical points are points where the derivative of the function is equal to 0 or undefined. So let's start by subbing in the derivative equal to 0. And now we can cross multiply the denominator. So we get 0 equals t squared minus 1. And now we can add 1 to both sides. The ones on the right side get cancelled out. So we get 1 equals t squared. And now we can apply square root to both sides. So we get t equals plus minus 1. So this function has two critical numbers. Now we should also set the derivative equal to undefined to find the critical points that make the derivative undefined. So this rational function for prime of s at t will be equal to undefined if the denominator is equal to 0. So we can set the denominator equal to 0 and then solve for t. So we apply square root to both sides. So we get t equals 0. So at t equals 0, there is a vertical asymptote. So that's why the derivative of the function is undefined at t equals 0. Now we can find the critical points by subbing in these t values at which the derivative is equal to 0 in the given function. So let's start with s at negative 1. So that will be negative 1 square plus 1 over negative 1, which is equal to, so 1 plus 1 over negative 1, which is equal to just negative 2. So that critical point is negative 1, negative 2. Now we can sub in t as positive 1. So we get 1 square plus 1 over 1. So this is just positive 2. So the other critical point is 1 comma 2. Now we have to use the first derivative test to find whether the function is increasing or decreasing on both sides of these critical points. So we can use the number line method. So first we can show the critical numbers. So negative 1 and positive 1. So now we have to find the test values on both sides of these critical numbers. So on the left side we can use negative 2. On the right side of negative 1 we can use negative 0.5. Now there is a vertical asymptote at t equals 0. So between 0 and 1 we can use positive 0.5, and on the right side of 1 we can use the test value 2. So we have to sub in these test values in the derivative of the function. And if the derivative is greater than 0, that means the function is increasing. And if it's less than 0, that means the function is decreasing. So we can use this equation. So we can use this equation. So now we can start with negative 2. So prime of s at negative 2 is equal to negative 2 square minus 1 over negative 2 square. So the numerator number will be equal to 3. So it will be a positive value because negative 2 square is 4 and the denominator is positive. So the overall value will be positive. That means the function is increasing on the left side of t equals negative 1. Now we can use negative 0.5. So we'll get negative 0.5 square minus 1 over negative 0.5 square. Now negative 0.5 square is 0.25 and 0.25 minus 1 will give us a negative value in the numerator and it will be positive in the denominator. So the overall value is negative. That means the function is decreasing between negative 1 and 0. Now we can use the positive value 0.5. So it will be 0.5 square minus 1 over 0.5 square. So now we'll get a negative in the numerator and a positive value in the denominator. So the overall value will be negative. That means the function is decreasing between 0 and 1. Now we can use the last test value 2. So it's 2 square minus 1 over 2 square. So we'll get a positive value in the numerator, positive in the denominator. So the overall value will be positive. So the function is increasing on the right side of t equals 1. Now in this function, the degree of the numerator is 1 more than the degree of the denominator. So this function does not have a horizontal asymptote, it has an oblique asymptote. Now the given function is s at t equals t plus 1 over t. So in this function, the equation of the oblique asymptote is y equals t. So it's this term. Now we have to find whether the curve approaches the oblique asymptote from above or below, and for that we'll analyze this fraction 1 over t. So for a very big positive t value and very big negative t value, if this expression is positive, that means the curve approaches from above, and if it is negative, that means the curve approaches from below. So we can do the test. So limit, so t approaches negative 100, so this is on the left side, so 1 over t. So if we apply the limit, so 1 over negative 100, so this is a negative term. So that means on the left side, so the curve approaches from below. Now we can do the test on the right side of the t-axis. So limit t approaches 100, 1 over t. So if we apply the limit, we get 1 over 100, which is a positive value. That means on the right side, so curve approaches from above. Now we can use all of this information to sketch the function. So we'll start with the vertical asymptote. So the vertical asymptote is at t equals 0. So that's the y-axis. Now to the left side of this vertical asymptote, the curve approaches negative infinity. So like this. And to the right side of this vertical asymptote, the curve approaches positive infinity. And now there are no intercepts, and the critical points are -1, -2. So let's assume this is -1 and -2. So the point is here. And then the other critical point is 1, 2. So let's assume 1 is here and 2 is here. So the other critical point is here. Now at the critical point -1, -2, there is a local maximum because the function is increasing on its left side and decreasing on its right side. So that means we can show the curve like this, and on the right side going down like this. And at the other critical point, the function is the other critical point is a local minimum because the function is decreasing on its left side, so like this, and increasing on its right side. And now there is a oblique asymptote at y equals t, so that will go somewhere like this. And as per the end behavior, so on the left side, the curve approaches the oblique asymptote from below, which we have shown, and on the right side, the curve approaches the oblique asymptote from above. We can just modify a curve a little bit to show it moving along the oblique asymptote. So this should be the sketch of this function. So these are the steps you have to keep in mind to solve a problem like this one. So I hope you'll find this video useful. Please share it, like it, and subscribe to Homework Help. Thank you very much and have a nice day. Bye.